Okay. Mm-hmm.
你看到我啥样的？你还没进去啊？
People are still coming, so let's wait a little.
Yeah. Okay. Fine.
Yeah. Fine. Yeah, the slides are fine. We can see you. Okay. Hello, Milian. Bao, hello. It's nice that you could attend this seminar. So let's start the seminar. It's 2 p.m. London time. Let me introduce our speaker, L Zeng. He is not stranger for our school. Lindong visited us from December 2019 to June 2020. So he was with us at the very beginning of pandemic, and during that time and after that he worked, and before that he worked very productively. He published one paper recently in Journal of Fluid Mechanics, one paper in Physics of Fluids. Recently, he submitted paper to Applied Ocean Research, and he did many, I would say, many presentations at different conferences on the topic of his research. So the topic of title of today's presentation is on the slide. Hydroelastic wave and loads moving along an ice channel. So Lindong, please start your presentation. I will disappear, means I switch off my camera and microphone, so everything is yours, but I'm here. If something is wrong, then I will enter again. Okay, so please.
Yeah, fine. Right. Yeah, fine. Thank you, Professor. Okay, now I start my presentation. Hello, everyone. I'm Lindong, a PhD candidate from Harbin Engineering University. The topic of my presentation is hydroelastic waves and loads moving along an ice channel. Before I introduce the work I did, the motivation of my work should be clarified first. We all know that the waves will be induced when a vessel moving on the water surface. This wave is usually called gravity wave. If the surface of the fluid is covered by an ice sheet, the ice sheet will deform along with the water surface. Now, the bending force of the ice sheet and the gravity of the water together develop the wave. It is called the flexural gravity wave. The green picture shows the flexural gravity wave detected by satellites, which are caused by the movement of a truck on the ice sheet. For the flexural gravity waves induced by a moving load, this is a combination of the flexural vibration of the ice plate and associated gravitational waves in the water. When the velocity of the load is close to the minimum phase speed of the flexural gravity wave, the water ceases to support the ice sheet and support is achieved only by the elastic properties of the ice. The amplitude of the flexural gravity wave increases sharply, and with a sufficient load, destruction begins. The power consumption is several times lower compared with icebreaker and icebreaking attachments. This method of ice destruction is known as the resonance method. The resonance method is usually performed with an air cushion vehicle, which is promoted for breaking ice cover in shallow water regions, where the icebreaker cannot operate due to the limitation of water depths. The frozen river with vertical words on both sides is the potential scenario for ice breaking by a moving load. Also, the ice tank test is a significant means to study the performance of a load moving along an ice channel, where the walls of the ice tank will have a great influence on the results. Thus, the topic of my presentation focuses on the ice channel, and due to the ice breaking efficiency of a moving load is shown depending on the critical speed of the flexural gravity wave. The problem of waves propagating along an ice channel and a load moving along an ice channel have been introduced. The work of waves propagating along an ice channel can provide helpful results and data to study the problem of a load moving along an ice channel. For the problem of a load moving along an ice sheet, the point work should go back to 1963, in which L studied a load moving along an infinite ice sheet floating on water. Then, many scholars developed this work, such as Davis et al., Takziva, Square. Fruitful results have been discovered, which shows that the ice sheet under the moving load can be broken, especially for the load moving with the critical speed of the ice sheet. Due to the air cushion vehicle is amphibious, it can move both on the surface of ice sheet and on water surface. So, some scholars studied the problem of load moving on the semi-infinite ice sheet and semi-infinite open water, such as Zaskaya's work. Besides, the ice sheet is non-homogeneous. Crack can exist in the ice sheet. The problem of a load moving along an infinite ice sheet with a crack is studied by Strava. The edge waves have been detected in their work. Crack in the ice sheet will form open water lead under the action of external loads. So, the work of a load moving along an ice breaking channel is considered by Strava and Scheer et al. The ice channel are very common in inland rivers, where the effect of vertical words cannot be neglected. So, as in the ice tank, thus, Sushimov and Kapapashia considered the problem of a load moving along an ice channel. It shows that the effect of vertical words on the ice responses is very significantly. Based on this, we conducted the work of a load moving along an ice channel with a crack in the ice sheet, which will be introduced later. On the other hand, three-dimensional waves propagating along an ice-covered channel are also worthy of attention. The problem of waves propagating along a channel fully covered by an ice sheet was considered by Harbin et al. And Batiev and Kapapashia. The problem of waves propagating along an ice-covered channel with a straight-line crack in the ice cover was studied by Leng et al. Then, we consider the problem of waves propagating along an ice channel with a lead of open water. This work was published at the Journal of Fluid Mechanics, which also will be introduced later. For the problem of waves propagating along a channel fully covered by ice sheet, the ice sheet is molded by an elastic ice sheet, with corresponding edge conditions between ice sheet and vertical words. The hydrodynamic pressure acting on the lower surface of the ice sheet is described by the linear ballooning equation. The fluid in the channel is assumed as ideal and incompressible. The flow is irrotational. Thus, the velocity potential can be introduced and satisfied the Laplace equation in the fluid domain. The impenetrable condition at the channel walls and bottom should be satisfied. Also, the linearized kinematic boundary condition at the upper boundary of the fluid should be satisfied. For the propagating waves, we assume that it's the sinusoidal waves propagating along the channel. Then we can write the form of propagating wave as the profile function across the channel, multiply the cosine function along the channel. Using the kinematic boundary condition, the form of a potential also can be written in this form. Once the ice sheet is uncontinuous, for example, a lid of open water in the ice sheet, then the hydrodynamic pressure is equal to 0 in the region of open water, and the free edge condition of the ice sheet should be added here. Particularly, if the width of the lid tends to 0, then this problem becomes waves propagating along an ice channel with a crack. Similarly, the fluid in the channel satisfied the Laplace equation and the corresponding boundary condition. Assuming sinusoidal waves propagating along the channel, then we can substituting the equation of the propagating wave into the upper boundary and of the channel and the Laplace equation. Equation relating to the wave profile, wave profile across the channel and the potentials across the channel can be obtained. For the ice sheet deflection, we can assume it's a superposition of a series of eigenfunctions. The eigenfunctions are the solution of the spectral problem, which is derived from the equation of the upper boundary of the channel. Note, this eigenfunction is orthonormal. Then we can solve this problem and get the expression of the eigenfunction. We can plot the curves of the eigenvalues lambda n vary with the wave number and the eigenfunctions for given wave number. Here the parameters are non-dimensional. Substituting the series of the ice deflection across the channel into the upper boundary condition and considering the linearized kinematic condition, we can get the integral condition at the upper boundary. Here the coefficients Fn are undetermined. For the upper boundary, value problem of velocity potential in the channel, the boundary condition at the free surface z equal to 0 can be replaced by the integral condition. According to the form of the integral condition, we can write the velocity potential in a similar form. The velocity potential big phi n is a solution of the boundary value problem. Due to the eigenfunctions cosine here can be obtained from the spectral problem in the last slide, the solution of the velocity potential big phi n can be derived. Then only the coefficient Fn in the form of the velocity potential is undetermined, which is the same as the series solution of the ice deflection. By using the kinematic condition at the upper boundary z equal to 0, we can establish the relationship between the solution of the velocity potential and the series solution of the ice deflection in the ice cupped region. Multiplying both sides of the equation by eigenfunction psi m and integrating in y from a to l and considering the orthonormal condition of the eigenfunctions, a system of matrix function can be obtained. We move the right part of the equation to the left, then a homogeneous equation is derived. By solving this equation, we can derive the dispersion relation of the flexure gravity waves, wave profiles across China, including the ice deflection and water elevation, and also the group and phase space of the fracture gravity waves. Also, the critical speed of the fracture gravity waves can be calculated. Here, I shall show some numerical results of the waves propagating along an ice channel. For waves propagating along a channel fully covered by ice sheet with and without a crack, was investigated by some scholars. The dispersion relations of the fracture gravity waves are presented here. The case of waves propagating along a channel fully covered by ice sheets with a crack is used to verify our method. It shows a good agreement. The dispersion relations increase with the wave number increases. We show the dispersion relation for waves propagating along a channel with a lead. The width of the lead is equal to 1.1 meter here. The first 5 modes are presented here. The left figure is the result for ice thickness with 5 centimeters. The dashed line are the results for the rigid model. The ice was treated as a rigid plate. We can see that the dispersion relations of ice thickness with 5 centimeters close to that of rigid plate model when the dimensionless wave number of the fracture gravity wave is larger than 6. The right figure is for ice thickness with 10 centimeters. It also shows a similar phenomenon, but it close to the dispersion relations of rigid plate model when the dimensionless wave number of the fracture gravity wave is larger than 4. Here we make a comparison to demonstrate the effect of open water lead on the dispersion relations. The dashed line here represents the dispersion relation of width of the lead equal to 0. The dotted line represents the dispersion relation of width of the lead equal to 1.1 meter. The solid line represents the dispersion relation of an infinite ice sheet. The dispersion relation is calculated by this equation. The dashed dotted line represents the dispersion relation of open water. It calculated by this equation. So if we define the wave number big K asterisk equaling to the square root of small k asterisk square plus small ky asterisk square, then we can clearly understand the characteristics of waves propagating along an ice channel. We note that the solid line and the dashed dotted line divide this chord plane into 3 regions, 1, 2, 3, and if the wave in the real number, and in the region 2, so wave number ky is in the region 1, the wave number ky is a real number, so it means the waves can propagate across the channel. The waves can propagate deeply into the ice, and in the region 2, the ky is the imagined number, so the waves cannot propagate deeply into the ice. The phase speeds of fracture gravity waves propagating along an ice channel was investigated here. The left figure shows the phase speeds of width of the open water lead A equal to 1.1 meter. Note that the phase speed of the first mode decreases monotonically with the wave number increases, while the variation of the phase speed of the higher mode is more complex. The phase speeds are monotonically decreasing and increasing and decreasing. Also decreasing, increasing, decreasing, increasing, decreasing. So the phase speeds are monotonically decreasing and increasing repeatedly for higher modes. For width of the lead being 0, the phase speed decrease first and then increase with the wave number increase. According to the definition of critical speed, we can find that more than one critical speed can be found for ice channel with a lead. We will be curious about how this critical speed will change with the parameters. First, we investigate the phase speeds of the first and the second mode for different ice thickness. Here we find that the phase speed tends to decrease monotonically for the second mode as the ice thickness increase. However, the phase speed for the first mode always decrease monotonically with the wave number for different ice thickness. Besides, we should note that the phase speeds are approximately equivalent for short wave and different ice thicknesses. Then, the effect of width of the open water lid on the phase speed is investigated. Here we find that the phase speed tends to decrease monotonically for large widths of the open water lid. For the middle widths of the open water lid, the phase speed first decrease with increase of the wave number, then increase, and then decrease again. This indicates that two critical speeds can be found for these cases. According to the analysis of the effect of ice thickness and the width of the lid on the phase speed, we can plot the curves of the critical speed value with the ice thickness and the width of the lid. For the case of half width of the open water lid being 1.1 meter, the first mode of the phase speed decreases monotonically with the wave number for different ice thickness, so no critical speed can be found. But the two critical speed can be found for the second mode. It increases with the ice thickness increases. For the case of ice thicknesses being 5 centimeters, the critical speed of the first and the second mode vary with the width of the open water lid shown here. We can find that the second critical speed of each mode will appear only when the width of the open water lid is greater than a certain value. But the second critical speed of each mode will merge with the corresponding first critical speed here when the width of the open water lid is smaller than a certain value. One should note that two critical speeds merge, providing a point on the dispersion curve where both the first and the second derivatives of the phase speed with respect to the wave number are zero. This is a very special point. Here we display the wave profile across the channel. The ice deflection are superposition of the eigenfunctions. Because the wavelength of the incident wave is relatively long at this case, the ice plate still undergoes significant deformation near the channel walls. After knowing the propagation of law of flexural gradient waves in the ice channel, we can use it to analyze the ice sheet response caused by a load moving along the ice channel. For a load moving along a channel fully covered by an intact ice sheet was studied by Sushimov and Kapapashia. Here we study the ice responses caused by a load moving along the ice channel when there is a crack in the ice sheet. We consider the stationary problem. The coordinate moving together with the load is established. The ice sheet is molded by viscoelastic plate in the moving coordinate system. The clamped edge condition at the channel walls. We consider the crack located in the center of the ice channel, so the free edge conditions should be added along the crack. The external pressure big P is described by a rectangular load. The fluid in the channel has the velocity potential phi and satisfies the Laplace equation and the corresponding boundary conditions at the channel walls, bottom, and the upper boundary z equal to 0. Here's a term with tau and with tau, the retardation time in the ice plate equation corresponds to the damping of the ice plate. It makes waves and the velocity potential decay to zero in the far field. It shows the width of the channel at the length scale and the magnitude of the external pressure at the pressure scale. Square root width of the channel divided gravity acceleration at the time scale. Square root of the gravity acceleration multiply width of the channel at the speed scale. Then we can write the dimensionless problem. The flow rate transform along the direction of the channel is introduced to solve the dimensionless problem. The ice deflection in the form of flow rate transform can be written as a series solution, in which the eigenfunction percent are the solution of the spectral problem. Then we need to substitute the series solution of the ice plate into the ice plate equation. Then we need to solve the velocity potential. The velocity potential small phi can be written as a series solution in terms of the kinematic boundary condition at the upper boundary. The velocity potential big phi are the solution of the boundary value problem. At this time, only the coefficient of big phi in the ice plate equation is undetermined. Considering the orthonormal condition of the eigenfunction percent, the ice plate equation can be transformed into a non-homogeneous system equation with the coefficient big phi to be determined. Solving this matrix equation, we can calculate the ice deflection using the theoretical solution of the ice deflection and the strain distributions in the ice plate here. Next, we shall present some numerical results with respect to the ice deflection and the strain distributions. The phase speeds of the fracture of the hydroelastic waves are helpful to explain the ice response caused by a moving load. Here, the dashed dotted line is the hydroelastic wave dispersion relation of hydroelastic wave predicted by the shallow water approximation. We show here is to indicate that the shallow water approximation only verified for very small wave number. For loads moving at 8 meters per second, here the green line, and we can see that the load speed have two intersection points with the hydroelastic wave, which corresponds to short wave and a long wave. This also reflected in the ice deflection, where the short wave propagating in front of the load and the long wave propagating behind the load. The wavelength of the ice deflection is equal to the wavelength corresponding to the intersection of the hydroelastic wave curve. Here, the case of the ice sheet with and without a crack are presented. We can see that the wavelengths of ice deflection for these two cases are close to each other due to their first mode of the phase speed is close to each other. But the moving load induces greater wave amplitude and larger strain near the load for ice sheet with a crack. For load moving at 18 meters per second, the ice deflection of ice sheet with and without crack are very different. The deflection amplitude of ice sheet with a crack is much larger than that of intact ice sheet. Coincidentally, the maximum strain along the center of the channel is the same for these specific conditions. The three-dimensional contour map of the ice deflection and strain distributions are presented here. The half plane represents the results of no crack, and the lower plane represents the results of with crack. We can see that the range of ice deflection is larger for ice sheet with a crack and load moving at 18 meters per second. In terms of the phase speed of hydroelastic wave, we can get the critical speed of the hydroelastic wave. The first and the second critical speed and the critical speed for long wave are given here for ice sheet with and without a crack. Then, the maximum ice deflections and the minimum ice deflection for different load speed are detected. We can see that the maximum ice deflection peaks at the critical speed for long waves for ice sheet with and without a crack. The ice deflection peaks locally for load moving near the first critical speed. The maximum strain along the central plane of the channel and the channel walls, and the maximum strain in the ice sheet are also detected for ice sheet with and without a crack. Here we can see that the maximum strain in the ice sheet is equal to the maximum strain along the center of the channel for load speed smaller than the first critical speed. And the maximum strain in the ice sheet is equal to the maximum strain along the channel walls for load speed greater than the first critical speed. The strain in the ice sheet also peaks locally for load moving near the first critical speed for ice sheet without a crack. Note that strains at the channel walls take the largest value for load moving at the critical speed for long waves. For ice sheet without a crack, the strain along the center of the channel peaks at the critical speed for long waves. From above analysis, we have known that the maximum ice deflection occurs at 8.66 meters per second, which is equal to the critical speed for long waves, and the minimum ice deflection occurs at 8.65 meters per second. Here we present the three-dimensional waveform for these two load speeds. It is seen that the ice deflection differs significantly for these two speeds, even though their values differ only by 0.01 meters per second. For load moving at critical speeds for long waves, the ice deflection under the load equates the static deformation of the free surface. This means that the moving load will be greatly elevated and may have an obvious effect on the operation of structures. Here we present the ice deflection and strain distribution along the center of the channel and along the channel walls for two load speeds. One is 3 meters per second and one is 9 meters per second. These two speeds are 3 meters per second are smaller than the first critical speeds, and 9 meters per second are larger than the critical speed for long waves. We can see that for load moving at 3 meters per second, the ice response is localized, and for load moving at 9 meters per second, the ice sheet only oscillates in front of the load. The reason is that the load speed 9 meters per second only have one intersection point with the hydroelastic wave. We find that the minimum ice deflection at y equal to 0 is not exactly under the load, but at a certain distance behind the load for latent time equal to 1 second, and the extent of significantly ice deflection decreases with increase of the retardation time of ice for supercritical speeds. The maximum and minimum ice deflection and the maximum strain are presented for retardation time equal to 10 milliseconds and 1 milliseconds. The deformation amplitude of ice sheet increase with retardation time at the first critical speed. Note that the amplitude of ice deflection at first critical speed exceeds that at second critical speed for retardation time equal to 1 milliseconds. The second critical speed is detected here. The maximum and minimum ice deflection oscillates for the load speed between first and the second critical speed. The strain near the critical speed strongly depends on the retardation time, but the maximum strain in the ice sheet equal to the maximum strain along the center of the channel for load speed smaller than the first critical speed. The maximum strain in the ice sheet equal to the maximum strain along the channel walls for load speed greater than the critical speed for different retardation time. The effect of the load characteristics on the ice responses is analyzed here. In terms of the maximum strain along the center of the channel and the channel walls for these three different aspect ratio of the load, we can find that the ice breaking ability of a load could be affected by the aspect ratio of the load, but the optimal ice breaking speed will not be affected by the aspect ratio of the load. Then, we further analyze the influence of load aspect ratio on ice breaking ability of the load. Here we give the maximum and the minimum ice deflection vary with the aspect ratio of the load for different load speed. We can find that the minimum ice deflection is more obvious affected by the aspect ratio of the load at the first critical speed, while the maximum ice deflection is more obviously affected by the load aspect ratio at the critical speed for long waves. For the maximum strain along the center of the channel and the channel walls, we can find that the maximum strain along the center of the channel is more obviously affected by the load aspect ratio at the first critical speed, while the maximum strain along the channel walls is more obviously affected by the maximum strain along the channel walls at the critical speed for long waves. Besides, the more the load is elongated along the channel, keeping the total load constant, the larger the strain in the ice sheet. But the ice breaking ability of a load moving with a constant speed does not continue to increase if the aspect ratio of the moving load is larger than 10. Here we analyze the influence of the water depth on the ice responses. Before we analyze the ice responses caused by the moving load, the phase speed of the hydroelastic wave for different water depths should be shown here. And here is the first critical speed. And here the critical speed for long waves. And here is the second critical speed. And then we plot the maximum. We plot the maximum and minimum ice deflection for water depth equal to 2 meters and equal to 10 meters. We also note that the maximum ice deflection occurs at the critical speed for long waves, and the minimum ice deflection occurs slightly smaller than the critical speed for long waves. Also, this phenomenon also can be observed for water depths equal to 10 meters. So we can conclude that this phenomenon is independent on the water depths. Also, the maximum strain along the center of the channel and the maximum strain along the channel walls, vary with the load speed, also be presented here for different water depths. We can see here the smaller the water depths, the larger the strain occurs along the center of the channel, which also indicates that a moving load is more suitable for ice breaking in shallow water. This explains why the air cushion vehicle have a higher ice breaking ability in shallow water. And here we analyze the influence of the ice thicknesses on the ice responses. Also, we presented the hydroelastic phase speed of the hydroelastic wave and calculated the critical speed for different ice thicknesses. And also the maximum and minimum ice deflection vary with the load speed for different ice thicknesses presented. Similar phenomenon also be observed. The maximum ice deflection occurs at the critical speed for long wave, and the minimum ice deflection occurs slightly smaller than the critical speed for long wave. For ice thickness which equal to 20 centimeters, similar phenomena also be observed. As to the maximum strain along the center of the channel, vary with the load speed, and the maximum strain along the channel walls, vary with the load speed, also presented. We can see here for thicker ice, the maximum strain is smaller. Here we find here the dashed line represents the yield strain of the ice sheet. We can see for ice thickness equal to 20 centimeter, the load cannot induce the ice strain larger than the yield strain. So we can conclude that the moving load cannot break the ice with 20 centimeters. We also can find that the curve is very flat for subcritical speed. For the load speed close to the critical speed, the maximum strain increase sharply. This also indicates that the moving load can improve. The ice breaking ability of a moving load can increase sharply only for the load speed moving near the critical speed. And a similar phenomenon also can be observed for maximum strain along the channel walls. That's all my presentation. Thank you for your listening.
Thank you very much, Lindong, for your presentation. Was many results, many figures. We have time for questions. Yeah. So, Lindong, what's time in your place now?
It's 9:33 p.m. 9:43. 9:43.
9:43. All right. Yeah. And you are speaking from the PGR room, right?
Sorry?
you are speaking from the room, which is for PhD students at your university. Is it right?
Yeah, yeah.
And so I can see that other students, they are still there, even it's almost 10.
Yeah. They are ready to go to the dormitory.
Okay, but still not there.
Yeah.
Still working or doing something. Yeah,
They are ready to
interesting.
left the office now.
Ready. Okay. So please, any questions? Please, yeah. Yeah. Okay. Then yeah, Peter, please.
Thank you,
Just
Sasha.
unmute yourself. Yeah,
Can you hear
hello,
me? Sorry,
Peter.
thank you. Very nice talk, thank you. I wanted to ask, when you had profiles with your water in the middle of the channel and ice at the edge of the channel, it seemed to be the case that you weren't imposing a continuity of position on the boundary, on the two phases you go across that boundary. So I'm just wondering what happens if your water height ends up above the ice at the edge. Because it would spill over on top of the water ice at that point, will it?
Yeah. In the lead, the water elevation might be higher than the ice deflection, so the Overwatch phenomenon can be occurred, but we didn't consider this phenomenon in our model. So we only can show that the water elevation is higher than the ice deflection near the free edge. Yeah.
But it did look like the water did get higher than the ice in the simulations.
Yeah, that's a good question. Yeah, but this is a reality phenomenon. But we can't solve this problem now. So because our the assumption of our problem is that the ice plate and the water elevation will be continuous, no convectivity, no. Yeah, the ice deflection and the water will always contact all the time. So even though near the edge, the water elevation and ice deflection is uncontinuous, we also didn't consider this problem. Yeah.
So just go back. It looked like there was that jump in the vector discontinuity.
Yeah. Peter, I'm not sure that yeah, it's right what Lindong says. He, I believe, was talking about possible separation of water surface from the ice, from the plate. So that is because water can go up, and also it can go down. And if it's go up, it's possible that it finally end up on the ice. But if it goes down, that it's possible that the water kind of move towards the wall. Right. So and then the wetted part is say function of time, or changing periodically in the case of waves. So this is complicated. Both phenomena are complicated. Yeah. And overwashing and that kind of cavitation. Actually, it's not cavitation. Oh, it's called ventilation, I believe. When the part becomes so that is complicated. However, the all problems studied by all problems presented today, they are linear, right? So we always can think about tiny tiny waves that kind of thickness of ice is larger than the amplitude of wave. So but that is very interesting questions. And I remember papers by Falkenson, I believe, about slamming of floating large elastic plates in waves. And also it's important issue, that slamming for so-called floating solar batteries. if we have the farm of solar batteries offshore, and this is the hot topic these days, because I mean, the idea is to place the solar batteries, but many of them are offshore, but there are waves. So how to protect the structure and batteries from that waves? And indeed, it's possible. The part of that kind of farm, solar farm, is exit water and then enter water again. Yeah, and only on the edge. So then this is very much related to your question with respect to the presentation by Lyndon. It's complicated and it's non-linear. It's non-linear.
Thank you, Sasha. Thank you, Lyndon.
Complicated.
Thank you for
There are
question.
many interesting question, open question. Yeah, many indeed.
Yeah. Due to the limitation of our assumptions, so we can sort of consider this phenomenon.
Yeah.
Okay.
And also I would say, if there are no open water, then it's kind of okay. I mean, linear approximation is okay, because the large deflection, large ice deflections, they are likely to break ice, right?
Yes.
So, and our assumption of continuity is not applicable anymore. But with water, with open water, the situation is different. So for ice deflection, yes, it's still small, but water elevation could be relatively large. And this is why this problem of hydroelastic waves, both in ice and in water, it's challenging. Yeah, because it's gravity waves or hydroelastic waves or both of them. So it's not it's challenging how to distinguish.
Yes.
Yeah. Thank you. Any other questions? I have, Lindo, I have two questions. But they are actually about the same things. So when you did calculations and you presented your results, your results, they are, say, very sensitive to small change of the velocity of the load or small change of other things. Right? So this means that your calculations should be kind of very accurate.
Yeah.
So how did you arrive at such calculation of high accuracy? How you checked that your simulations are well and or are accurate? And with this respect, you know, actually, finally, in all your problems, you arrive at matrix equation, and you solve that equation. Either the matrix equation with zero right-hand side, and then you find the dispersion relation and you analyze properties of that wave. Either the right-hand side is not zero, and then you find the deflection caused by, say, moving loads. Right? But the I believe the matrix you used in your calculation, it should be large. I don't know, say 20 by 20 or 100 by 100. So the many coefficients to be calculated. How did you calculate? So could you explain a little bit about your calculations?
Yeah. So yeah, for waves propagating along the channel with the lead, the matrix with nearly 400 and 500 terms multiply 400 and or 500. So it's a very large matrix. We calculated by the Gauss eliminated method. And for the problem of a load moving along the channel, the matrix A check editor is relatively small, so we choose the 20 multiply 20 is enough, and we also calculate the term 50 multiply 50 is is nearly get the same result. So we believe that 20 modes is enough for our calculation.
Okay, so this means that you checked your accuracy by increasing a number of terms, increasing the level of approximation.
Yes.
And comparing the results up to arriving at certain accuracy. I don't know, 10 minus 6. What's the accuracy? What was your critical value of accuracy?
We also calculated the absolute difference and the relative error for the for the results. For the absolute error, it might 10 minus 4, maybe this, and the relative error may be 0.1%.
Once again?
Yeah, the relative error is 0.1%. So I believe the accuracy is
1%.
enough.
Okay.
Yeah, 0.1.
Okay. Yeah. Okay. And what you said, just to confirm, is it right that for waves in the channel with a lead, we need to retain more terms than for ice channel without a lead?
Yes. For ice channel with a lead, we need a little more modes to calculate to obtain the accurate results.
Okay. And also the presence of lead significantly changes dependence of phase speed on wave number, right? So leading to the double critical speeds or multiple critical speeds for the same mode. So that is the this is I believe new result, and it's not you cannot find this result for ice sheet of infinite extent as it was done by many others. Any other questions? I just checking. Not yet. Okay. Okay.
Can I ask a question?
Yes, please. Yes.
That is one of your first slide was that the phase curve with the several maxima and minima. Did you calculation that the body motion closer for this this speed between the several maxima and minima? What is the new novelty of the several maxima and minima? That is also means that the several critical speed nearby.
Sorry, could
I believe I can answer. So I believe I can answer this because
could you repeat the question for Don?
No, everything right. So in this presentation, the only waves were shown for ice channel with lead. There were no moving cloud. Right? So and as I understand, I could be wrong. This question to Lingdong that research on a load moving along the ice channel with a lead, that research has not been done yet.
Had not been done.
That is a future work.
So and then the question from Tatiana is kind of for future work. And indeed, it's because Lindong analyzed that waves. Now it's time kind of to combine these waves to construct solutions for more complicated problems. And indeed, the that special conditions when several critical speeds they are close to each other should be simulated to find, as Tatiana said, what's special about these cases. Yeah, that is very good suggestion.
Maybe not for the moving load, but it is also for the set of the wave. Maybe new set of the wave appear here. Maybe not. That is interesting to investigate.
Yeah. So again, Lindong is if we, I'm not sure, it could be in your files somewhere how a wave with double critical speed looks like.
Hot wave with double critical speed.
Yes.
So you mean the wave induced by a moving load?
No. Just wave. Just wave. So you calculated waves. You calculated for different modes, for different conditions, and for different wave numbers. Then you identify for a certain mode, identify conditions where the critical speeds merge. Two critical speeds merge, right? So then you know this condition. You know that value of the wave number, and for that value you can find per file.
Yeah.
Right, and then you can compare this per file with wave profiles when the two critical speeds are separated. Right?
Yeah.
Then you can, yeah, that is kind of easy because you have everything already for that.
Yes.
And and then there could be something interesting, could be not. It's not clear. It's more likely that not more likely, but we do expect another features of deflection when the two critical speeds merge. But as to deflection or waves, it's not clear. But indeed, there could be something interesting.
Yeah, I can compare the wave profiles.
Yeah, I don't remember because you did many calculations different conditions. But did you? I don't remember. If just check your files, and if not, it would be interesting to do that. And in particular, we can think in terms of that workshop, WWFB, floating bodies next year, and in April. So then it could be interesting. If there are interesting results, there could be interesting presentation at that workshop. Yeah, thank you, Tatiana. It's very good, very good. Both suggestions are good for future work. Okay, if Lindong has time to continue with this very interesting case.
Yeah. Okay. Yeah. Thank you for your question, Tatiana.
Yeah,
Nice suggestion.
I have some other questions, but we should finish. I will write in email that questions. They are more technical. Okay, so if there are no more questions, then we close the seminar.
Thank you, Sasha.
Yeah.
Thank you very much. Thank you, and Tatiana for supervising Lindong's very excellent work. Yeah.
So that is from good, nice words from supervisor of Lindong, Professor Bao Yuni. Thank you, Bao Yu. Thank you. And there are some chat, but Lindong, I believe you can see the chats and
I see.
People are leaving and just saying thank you for the nice talk. Thank you for the very nice talk. Thank you for the nice talk. So that you can see that, and indeed the presentation was very good, very informative. So okay, then we close the session.
Okay.
Okay. Bye.
Thank you.